All right, good morning, everybody.
Good morning.
Let's see. All right, let me go ahead and share my screen. I think we got over half of y'all here, so we're gonna get cracking. So the exam is up. It'll be available after class is over, and there's a it's actually in two parts. There's a multiple choice part, and then there's also a written part. So make sure you do both, and then both due at this, on Sunday by 11:59. So let me go ahead and share my screen, and we're gonna jump in. So let me let's start out addition, and we talked about conjugated dienes, and so we're gonna start a section dealing with reactions of conjugated dienes.
Dr. Russell,
Yes.
this supposed to be on the next exam or this exam?
No, this part that we're doing today is on this exam, and then the other part will be on the next exam. And I did that on purpose because what we're getting ready to talk about today, we've seen it before in part one. So it shouldn't be something that's esoteric or brand new. It's something that you should be familiar with. And there are two reactions we're going to talk about, but the one we're doing today, you've seen electrophilic addition of HX to an alkene before. We've seen that in part one, studied the mechanism, studied everything. So we're just adding a couple of little extra pieces to it today. So we're going to do today addition of HX to a conjugated diene. All right, and then we're also going to study cyclo addition, but we won't do that. We'll start that on Monday, and that'll be on the fourth exam. Yeah, the fourth exam. So you remember from part one, or you should, when you have a alkene like so, and you add HCl, let me substitute it, HCl, HBr, or any type of acid, and add it across the alkene, right? It follows Markovnikov's rule. It goes through a carbocation intermediate, right? I'll just go ahead and show the mechanism real quick. So you add the alkene attacks HBr, rips off that proton. You form a carbocation on the most substituted carbon. This is all from part one. The H is that got picked off is here. And then bromine attacks as a nucleophile. It attacks that, let me see if how can I show that? I'll just show it like that. It attacks that carbocation, right? And so you end up with an alkyl halide. We learned that in part one, right? And so when we talk about a conjugated diene, the only thing that we're going to add to this is that you can control the products, which you should have seen if you watched that video that I sent on yesterday, right? So if you take a conjugated diene, like 1,3-butadiene, and you add HX to it, right? You're going to get two products. Somebody tell me what those two products are. If you watch that video I sent you, what two products are you going to get from this reaction? Anybody?
Is it a kinetic and a thermodynamic?
Yeah, you're right. You're right. You're going to get the kinetic and thermodynamic product. But before we talk about that, the kinetic product more than likely is going to be here. I'm just going to draw the products and then we're going to talk about the mechanism. And then the second product is more than likely going to look like this, right? Let me fix that up. Right, where bromine adds. Sorry about that. Bromine adds here. All right. So we're going to talk about how that happens in a second. And let me turn this to make this HBr so it makes sense. All right. So you're gonna, anytime you add HX to a conjugated diene, you're gonna get two products, right? The thing about this reaction is that the product distribution can be controlled by the temperature. And do y'all remember the what this term product or phrase product distribution means? Anybody?
It basically means how much product you're gonna get, like the ratio.
Two products. Yes, that's exactly. It's the ratio of the two products. That's all. It's not. It's a fancy term for percentage of each product. So you can control that product distribution by the temperature. All right. At low temperature, you get one product, which we're going to talk about in a second when we're going through the mechanism. And then at higher temperature. All right. So let's look at how it works. Right. This is not anything that you've not seen before. Right. Because when we studied alkenes in part 1, we went through a whole plethora of reactions that alkenes do. And the first one that we studied was adding HX, right? HCl, HBr, HI, whatever. Every halogen works except for fluorine. Right? We studied mechanism indeed. But for this particular reaction, right? And let me do with the alkene, because one of the things about reaction, both alkenes are equally susceptible or equally reactive. HBr, right? So my alkene is going to attack here because the alkene is the nucleophile in this case. HBr is the electrophile. Or you can say the alkene is a base. HBr, since HBr is an acid, it doesn't matter. You're going to do proton transfer in that first step. Now, the question for now is where the carbocation intermediate is going to be, right? That's always the question when you're using an alkene as a nucleophile to attack an electrophile, is the carbocation intermediate is inevitable. The question is where do you form it, right? So in this case, the intermediate for this reaction is always going to be an allylic carbocation, right? You should have seen that in the video that I sent. This is common to both products. Both products are going to come from the same place. Right, you got a allylic carbocation, which is a common intermediate to both what we call a 1,2 and the 1,4 product, which I'm going to explain in a minute. All right, any questions so far?
Dr. Russell,
Yes.
can you scroll up a little bit? My Wi-Fi kicked me out of the chat for a minute, so can you scroll up a little bit?
Mm-hmm. If you have a question, you got to unmute because I can't see the chat. I'm working from my iPad again. I kind of like this. It's much more efficient than having
Just a little bit more,
connection.
Dr. Russell. Like up a little bit more. Okay, I got it. Thank you.
All right. You're welcome. All right. So this allylic carbocation again is common for both products. Right, it's common to both products, right? So the bromine here, let me put my lone pairs in. Now you can see again, the bromine can attack here, like so, attack directly at the carbocation, right? And that's going to give me, let me move this out of my way so I can write. Right, we'll call this direct attack. Right, it can attack directly, and that's going to give me one product. It'll give me this one. Everybody see that or no? All right, or pick a different color, or I can attack here, like so, and shift the alkene over. So that's going to give me this product. Or bromine is here. Let me fix that up. Like that. Anybody not see that? That product we can call the resonance product. I'm going to show you why. Right, we're also going to give it another name too, but for now we're going to call it the resonance product. Right. If you look at that allylic carbocation, what would the resonance form look like if I asked you to draw the resonance form of that?
You would shift the double bond over to the
Shift
right.
it over like this, right?
Mm-hmm.
Like this. So that would
Yes.
give me this, wouldn't it? With the plus charge on this carbon. Is that right?
Yes, sir.
Do you see that product up here? How that if I drew the resonance form and bromine attacked at that carbocation, that's the product that I would get. Right. So that's why that's the easy way to think about the second product, is just to take the allylic carbocation and draw the resonance form, and then you'll know where to put bromine. Right. That's a fast and quick and dirty way to think about it. Right. But another way that we characterize these, we call this one the 1,2 product, and we call this one the 1,4 product. And I'm going to show you down here why. We started with this alkene, this side. All right, we started with that alkene. We're going to start numbering this system from there. So 1, 2, 3. Come on, finger. 4, right? So when we look at the carbocation, it's the same numbering. 1, 2, 3, 4. So bromine attacks directly here. Right, we call that 1,2 attack. Right, if bromine attacks here, right, or what we call the resonance product, that would be considered 1,4 attack. Right, so you got the 1,2 product, which is direct attack, and the 1,4 product, which is the result of what we call resonance attack, right? Because that's where the plus charge would be if you drew the resonance form. All right, any questions so far? All right,
No questions.
go ahead.
No, I said I don't have a question.
Okay. All right, so let's look at an example, and I want to show you the temperature part now, right? How you get one of these would be considered what we call a thermodynamic product, and one would be considered the kinetic product. Let's talk about that. So let me add another page here. All right, so we have kinetic versus the thermodynamic product. All right, and we're going to start with that same alkene, that same conjugated diene here. And we're going to treat it with HX, which in this case we'll stick with HBr. We already know. But here we're going to do, what I'm going to add in is the element of, well, I'm going to change the temperature. So let's say we did this at let's say we did it at negative 20 degrees. All right, so at negative 20 degrees, we're going to get both products still. We're going to get this product, and we're also going to get, let me move this on. We're also going to get this product. All right, but in this case, the ratio is going to flip, right? This product, let's say we get it at 80%. And then we form the 1,4 product and 20%, right? So this is at low temperature. And the product that we get at 80%, we're going to call that the kinetic product. Somebody tell me what that means. If you watch that video, what does it mean to be the kinetic product? Right?
Is
for
it a
this,
product that's formed faster?
yes. So the rate of reaction is faster, so it's the fastest formed product. Thank you. Right? It's the one that's formed the fastest. You only see this phenomenon, like kinetic versus thermodynamic product, if there's a competition, right? If there's some competition between two potential product, species, two potential products. If there's a competition, then sometimes you'll see this kinetic versus thermodynamic. The kinetic product is not necessarily the most stable, but it's the most readily accessed, right? So at low temperatures for this reaction, the kinetic product predominates because the 1,2 attack is faster than 1,4 attack, or direct attack is faster than resonance attack.
So could you say the kinetic product is more spontaneous than the thermodynamic one?
What do you mean by spontaneous? That's a good question. I just want to make sure that I understand it right so I can answer it the right way.
Okay, like it just happens, like it could, like we said, it happens quicker than the
More
other
readily.
one.
Yes.
Yeah.
Okay. Yep. That's exactly right. And the reason is because think about, let's go back up to the mechanism. To see it, how in the mechanism, the first thing we get to is that 1,2 the little carbocation, right?
Mm-hmm.
So since that carbocation already exists at low temperature, the fastest thing to happen is for bromine or whatever your halogen nucleophile is to simply attack that, right?
Okay.
There's a lot, and there's the reason for that is that the lower the temperature is, the less energy there is for that second pathway to start, right?
Okay.
So you get a little bit of that, but you're going to get more of what's already available, which is that allylic carbocation, which is already sitting there just waiting on the nucleophile to come in.
Okay.
Does that make sense?
Yeah. Yep. Thank you.
Yeah. So the kinetic product is happens faster because the barrier to that reaction, right, or the activation energy for that reaction is normally lower than the activation energy to get to the thermodynamic product, which I'm gonna show you in a second. I'll show you. It was in the video, but I'm gonna recap it. An energy diagram to make it make more sense. So the kinetic product predominates at low temperatures. And I'm gonna put this in here due to a lower delta G double dagger, right? That's delta G double dagger is my activation energy. All right. So a lower activation energy to get to that, or a lower barrier. That's another way to term activation energy or call activation energy, right? There's a lower barrier to that reaction, and so it happens faster. That's why you get more of it at low temperature. Are y'all following? Anybody got any questions about that? All right, let me put another page in here. Didn't realize I was gonna need this many blank pages. All right, so take the same reaction and warm it up. Let's say to room temperature. So warm it up to room temperature, and you'll see a shift in the product distribution. If you warm it up, and not necessarily it doesn't have to be, you can warm it. If you go from -20 to 0, you're going to see a shift, right? But if you warm it up to room temperature, then the product distribution changes. And normally it's going to change in favor of the 1,4 product. Right, it's going to change in favor of the 1,4 product, right? So the 1,4, in this case, we call it the thermodynamic product. Did I spell that right? Well, I'm tripping. Can't put that on YouTube. I'll be getting slandered for days. It's because my N is cursive and my M is normal. All right, so the thermodynamic product, that the definition or the terminology that we use for the thermodynamic product is that it may form slower, but it's more stable. So it's the most stable. All right, it's the most stable product. And it has a higher, right, a higher activation energy. But what are we doing by warming it up? What are we supplying that's not there in at low temperature?
So I don't know if this is right, but do you add the temperature to like kind of excite the electrons to do resonance?
Well, okay, so the excitation part, you can only excite electrons with how do I put this? With electromagnetic energy, like light energy. So you
Okay.
need like UV light or something like that too. But what you do is you do increase the amount of energy that's available,
Okay.
right? Every I think it's every 10-degree increase in temperature, I think it doubles the rate of a reaction every 10 degrees. So what you're doing is you are actually increasing the amount of energy that's available for bromine to go back and attack that other site.
Oh, okay, that makes sense. Yes.
So at low temperature, you think about it. Think about it. An ice cube, right? If you put liquid water in the freezer, it starts to freeze, right? What is that
Mm-hmm.
freezing? The freezing means that the particles have slowed down. Is that right? All of the particles that make up water, they slow down to a point, they become a solid, and the movement is very little. But when you warm it up, it goes back to a liquid because you added more energy to disperse those water molecules. So now they are more free because the movement is more, right? They're moving, they're vibrating more, and it's the same thing here. At low temperature, the movement between atoms slows down. It's that simple. But then as you increase the temperature, you also increase the energy that's available. And so the movement is a lot freer, and the atoms are able to vibrate a lot more at higher temperature. All right. So then you get more collisions, and then you get more pathways open. And so that's what's happening here. The 1,2 pathway is readily available at low temperature. The 1,4 pathway is not, because it takes more energy to get for that pathway to happen. But the moment you add more energy to the system, then you also make that other pathway more available. Does that make sense?
Yes, thank you.
All right. So down here, we can say that at higher temperatures, we open up the 1,4 pathway. And then the other part of this, when we say that it's the most stable product, if you look at the two products, how do we judge the stability of an alkene?
By how substituted it is?
Yes, that's exactly right. How the substitution pattern. Excuse me. So look at this alkene. How is it substituted? What would we call that? Is it substituted? Anybody? Look at what's attached. You got a group out here. Am I right? You got a carbon here attached to it, and you got a carbon here attached to it. All right. So in this case, it is substituted. What about the one up top? Here. What's the substitution on that one? You only got one carbon attached to it. Is that right? Everything else attached to it is hydrogen. I don't have them shown, but there are two hydrogens on that terminal carbon right here. Right? So that will be monosubstituted. Dang it, I hate when I run out of room like that. It's monosubstituted. So which one of those is going to be the more stable alkene?
The one that's disubstituted.
Disubstituted. The more the alkene is substituted, the more stable it is, because all those carbon groups are feeding electron density into those sp2 carbons in that double bond, which are more electronegative because of their hybridization state. All right. Any questions about the thermodynamic product? You can see how the shift in the product distribution is, again, we can control which product we get based on the temperature. Right? If we do it at low temperature, we can control that, and we can get the kinetic product as the favorite product. If we do it at high temperature, then higher temperature, then we can get the thermodynamic product. And this matters, right? Because when you think about that big giant Taxol molecule that I showed you earlier. Like, a lot of times the application of this happens, when you're doing synthesis. You might be doing a synthesis where you don't need the 1,4 product, but you need the 1,2 product. So you do it at low temperature. So you can get that product and isolate it and then use it as a precursor for another reaction. Same thing with if I need the 1,4 and not the 1,2, I just warm this up. And the thing about doing it under thermodynamic conditions is that you could really force all of the 1,2 to convert to the 1,4. If you watched that video last night, you saw that it had an energy diagram in there, right? So you have your intermediate, your carbocation intermediate here, and this is where my two products are coming from. Right, so and then we had a kinetic product. Right, and you can see it immediately. The kinetic product has a lower activate. This is the activation energy right here, and this is all stuff from part 1 that we learned when we did enthalpy, delta H, delta G, exothermic, endothermic. When we did thermodynamics, all of this stuff we learned already. So this is the activation energy to get to the thermodynamic product, and then this is the activation energy to get to the kinetic product. And remember, the activation is the activation energy that controls the rate. So the higher or lower activation energy is, the faster or the slower or faster the rate is going to be for a given reaction. I should make that a little bit, change that just a little bit. Right, and then you can see the difference in energy between even the thermodynamic and the kinetic product. You can see that too. Right, the kinetic product a lot of times is going to be higher in energy, but since it's more readily accessible, then that's what you get at lower temperatures. Right, so this is the kinetic, and then over here would be the thermodynamic. All right, so this is low temperature, and this is higher temperature. So what do you think about this? Like, how could I get, so let me not say that. So if I warm this up, what do you think about let me say it this way. How can I get the kinetic product to become the thermodynamic product? By warming up the reaction. Let's talk about that. Because you can't do that. That's how the product distribution changes, right? You get both products at higher temperature, but because the thermodynamic product is more stable, the equilibrium is going to tend to that side, right? Because under thermodynamic conditions, you have equilibrium. Under kinetic conditions, you don't. It's irreversible, right? And let me put that in here. All right, that's irreversible. So once you get the 1,2 product, you're stuck. But under thermodynamic conditions, everything is reversible. So how can I get, if it's reversible, how can I go from the kinetic to the thermodynamic? Cut this out because I don't want to run out of space. We'll put this on another page and discuss it. All right, so let's talk about that. And I think that'll be the last talk about. All right, so how do you interconvert between the kinetic and the thermodynamic product since under thermodynamic conditions or higher temperatures, right, the reaction becomes reversible? So let's think about that. So it's reversible now. And they both products come from the same intermediate. What do you think? If I start with the kinetic product, how do I get to here? What do you think? Right? How when we study substitution, how do we form, like for the SN1 type substitution, how do we get to the carbocation intermediate that reaction went through?
Loss of leaving group.
You lose your leaving group. Can we do the same thing here? Isn't this the same, in the same vein, to go from the halide to the carbocation intermediate? How would you show that?
So could you do resonance and then make the bromine go away? Like eliminate?
Yeah, you could definitely do that. You could definitely do that. And that's one way to think about it. But there's also, I mean, bromine is an excellent leaving group. Am I right?
Yes.
Yeah. And if I want to get back to that intermediate that I have shown, I can just show it leaving. Is that?
Mm-hmm. Yep. And think about that.
Mm-hmm. Now you're right though. You could show it that way. And I'm gonna show it. I'll put another page in to show that, because I'm glad you thought about that, because you could show it that way. You could show the resonance between, or it's called neighboring group participation. So you got the pi bond could shift over and cause that bromine bond to break, and then the bromine can come back and attack the other carbocation. You're right. But in this case, if I just want to get back to the intermediate, right, bromine can leave via like a SN1 pathway. Right, you just lose your leaving. It's a leaving group. You lose the leaving group, you get back to the intermediate, and then now, since you're at higher temperatures, the intermediate can then undergo 1,4 attack, right, instead of 1,2 attack. Are you following? So we could start with the actual 1,2 product, lose the leaving group, go back to the intermediate. So cross the barrier back over to the intermediate from the product. And then that intermediate can then get converted into 1,4, into that 1,4 product. Right. But yeah, but what you said also is a plausible mechanism as well. So you said that we could do this. I'll put this in here. My kindergarten teacher would kill me. This is something my handwriting. So we can go here. Is this what you were saying? To do it that way?
Yes.
Mhm.
But would it just take longer if you did it like that?
Not necessarily. Not necessarily. It's that's why I said it's a plausible pathway. Because it could happen either way. And there's a way to probe it too. You could probe it by NMR. Right? If you saw, and we talked about NMR in lab last year, but if you saw of the other pi bond forming by NMR,
Mm-hmm.
because the protons would be different, the coupling constants, all that. I don't want to get too deep in the weeds, but you can tell, you can see if it was this pathway. You could do a mechanistic study by NMR, and you could see if it was that. So it would be, so you're saying we could get this. Yeah, I agree with that. You could think about it that way too.
Okay.
Mm-hmm. And then boom, this comes right here in the text, right? And gives you your 1,4 product. Yep. That's a plausible pathway. So it's not a wrong answer. It's actually a great answer.
Thank you.
Mm-hmm. All right. Any questions about anything? So we know, let me just recap what we talked about. So we talked about adding HX, electrophilic addition of HX to a conjugated diene. We know that it goes through a common intermediate. The allylic, you can't form the other carbocation because you can't stabilize it by resonance, right? So the plus charge will never be here. It'll never be on this carbon right here, ever, right? It's always going to be allylic. And so, excuse me, we know we go through allylic carbocation. We know that you get two products, the 1,2 and the 1,4 product. We also know that you can control the product distribution by the temperature. At low temperature, you get the 1,2 product as the favorite product. At higher temperatures, you get the 1,4 product as the favorite product. And what we also know is that you could also convert at higher temperatures. You can convert the 1,2 product into the 1,4 product, right? By going back to the intermediate, and then that intermediate reacting through the pathway that gives you the 1,4 product. All this is only possible when we temperature, and then at the same time increase the amount of energy that's available. All right. Any questions about anything that we talked about? I have we didn't even get to the questions in the handout, and I don't want to rush that. But let's just start the first part. So you see here, this is not symmetrical, right? So you got an alkene here, and you got an alkene here. So the product distribution, so here you're actually going to get 4 products, right? Because you can react either one of those alkenes. So if we take that first one and react it, let me show you what the intermediate is going to look like for that. Right, so that's our intermediate. That's the intermediate for if we react the alkene. I'm gonna put the highlight back in yellow so you can know that. We react that alkene that's highlighted in yellow, that part of the diene. That'll be my intermediate plus Br. And then if we reacted the one that's highlighted in pink, all right, this stays put, and then your plus charge is here, right? Because the intermediate is always going to be the allylic carbocation. So I'm not going to put the plus charge anywhere except for the allylic site. What does allylic mean again? Anybody? Because if you don't know that term, then it's going to be difficult for you to think about what allylic. Based on the silence, I think I've been speaking Chinese for the whole 45 minutes I've been talking. When we did allylic bromination, what was that? Why did we call it that? Doesn't it mean adjacent to a double bond or adjacent to an alkene? Yes. You can see that the plus charge here is the plus charge right there is next door to an alkene. It's on a carbon that's next to an alkene. You can see the same thing here, that plus charge is on a carbon that's adjacent to an alkene. So with a diene like this, you're going to actually get 4 different products depending on which alkene reacts. So in the last couple of minutes, let's see if we can figure that out. So what would the 1,2 product look like if alkene 1 reacted? Where's bromine going to attack? Is it going to attack directly at the plus charge, or is it going to attack somewhere else? If it's the 1,2 product. Wouldn't it attack here? That's what the 1,2 indicates, right? If we come up back to the alkene, this is 1, 2, 3, 4, because we're leading off with the alkene that's highlighted in yellow. All right, so it's going to attack directly at the plus charge, and the bromine is going to end up at that site. Like that. What about the 1,4 product? What is that going to look like? On this intermediate. Isn't bromine gonna come here? Then we just like do this on a different, it's a different molecule, but it's the same mechanism. Nothing has changed. Right? Nothing changes. The process stays the same. So this double bond now is going to be here. Shift it over just like we did up top. And then the bromine, I need to shrink this down or move it. Bromine end up here on this carbon, right? That was 1, 2, 3, 4. Just like that's 1, 2, 3, 4. Right? So the 1, 2, and 1, 4 products are going to be based on, well, each one will be based on temperature. All right. So I'm going to leave the other intermediate here. All right, I'm gonna leave that. You can put those products in because you're gonna get, this is for that second alkene. That'll be 1, 2, 3, and 4. So you should be able to draw those products. All right, we're gonna stop here because it's 9:59, and I got another class coming up at 10. Any questions?
Dr. Russell,
Yes,
did you ever do recitation yesterday or no?
I was in Zoom. Yes.
If you did you record it?
Nobody was there. I opened it up at like 7 and I stayed till like 7:30.
I have plans.
Normally, yeah, it's all right. Yeah, I was there. I should have sent an announcement out, but I was in there from like 7 to 7:30.
All right.
But if you have questions, you can always just email me or set up another time, and then we can do that. All right, go ahead.
So, if we have questions over the weekend, just last minute studying, will you be available to
Yeah.
for Zoom calls and stuff?
It should be never mind. I almost said something. Yeah, I'll be available. All right. Any other questions?